There is a machine buried under the border of France and Switzerland that smashes particles together at nearly the speed of light, and some people believe it may have made a black hole down there. Not a metaphor, a real one. A tiny knot of gravity, born underground, sitting somewhere beneath the farmland. Sit with that for a moment. A black hole on Earth, made by us on purpose in a tunnel we can drive through. It sounds like the opening of a disaster film, the kind where a scientist wipes his glasses and says the words nobody wants to hear. And yet the idea did not come from a film. It came from real physics. Serious physics, equations that serious people take seriously. That is what makes it worth your time. Not the fear, the reasoning. Because when you follow the reasoning all the way down, it takes you somewhere far stranger and far more beautiful than any disaster film ever went. So let us follow it, slowly, carefully, one step at a time. I want you to notice something as we go. The fear you might feel right now, that little tightness in the chest at the words black hole under Geneva, is not made of physics. It is made of stories. And the physics, the actual physics, is going to do something surprising to that fear. It is going to dissolve it and replace it with something bigger. And I promise you, by the end, you will not be frightened. You will be astonished. Because this is not a story about a machine that might kill us. It is a story about the strangest laboratory ever built, and about a wound at the very center of physics that this machine was made to probe. Let me tell you what most people believe, and then what is actually true, because the gap between them is enormous. Most people hear black hole and picture a monster, a cosmic drain, something that eats everything nearby and grows without limit. So if you tell them a black hole was made under Geneva, they imagine it swallowing the tunnel, then the town, then the planet. That picture is wrong from top to bottom. And the wrongness is the interesting part. A black hole is not a vacuum cleaner. It does not roam. It does not hunt. It has no more appetite than a rock. If you replaced our sun with a black hole of exactly the same mass, and that is a strange thing to picture, the Earth would not get sucked in at all. It would keep circling in the very same orbit, in the very same year, because gravity depends on mass and distance, and neither of those would have changed. It would get very cold and very dark, yes, but we would not fall. That single fact should already unsettle the monster in your head. A black hole pulls exactly as hard as any other object of the same mass, no harder. The only thing special about it is that its mass is crushed into so little room that if you get close enough, the pull becomes impossible to escape. Close enough, those two words carry the whole story. So before we talk about whether the machine made anything at all, we have to talk about how anyone could possibly know. How do you make a claim about something you cannot see, cannot touch, and cannot dig up? That is the real question. And the honest answer is that we never actually see any of these things directly. Not black holes, not particles, not the fabric of space itself. We see consequences. We build a picture of the world from the shadows it casts on our instruments. Think about how you know there is wind. You never see the wind. You see the leaves move. You feel the pressure on your face. You watch a flag snap. From those clues, you build the idea of wind, and it works so well you forget you never saw it. All of physics is like that. We watch the leaves move. The leaves, in this case, are numbers on a screen, tracks in a detector, faint flickers of light. Consider how we found the very first black hole ever confirmed. Nobody saw it. What we saw was a star, a perfectly ordinary bright star, swinging around in a tight circle as if it were dancing with an invisible partner. Something heavy was tugging on it. something we could not see. We measured the star's motion, timed its swing, did the arithmetic, and the invisible partner turned out to be far too heavy and far too small to be anything but a black hole. We read the leaves. We inferred the wind. And we have done this again and again since, in dozens of ways. We have watched two distant black holes spiral together and felt the tremor pass through the fabric of space itself, a ripple in space-time so faint it moved our instruments by less than the width of a proton, and still we caught it. We have even taken a kind of photograph, not of a black hole itself, which gives off no light, but of the bright ring of matter swirling just outside its edge, a dark circle framed in fire. Every one of these is the same trick. We never touch the thing. We read what it does to everything around it. Hold on to that, because when we ask whether that machine under Geneva made a black hole, we are going to answer it the same way. Not by digging, by reading the leaves. Now, here is the thing you must hold on to for the rest of this journey. Reality has layers. At the everyday scale, your intuition is a good guide. Things fall. Water is wet. A ball thrown will land where you expect, but go smaller, or faster, or heavier, and your intuition starts to lie to you. At the scale of the very fast, near the speed of light, space and time themselves bend and stretch. That is general relativity, our best description of gravity, where space is not an empty stage, but a flexible thing that curves. Clocks run slow near heavy objects. This is not a theory on a chalkboard. The satellites that guide your car know it. Those satellites sit high above us, where gravity is weaker and their clocks tick a little faster than clocks down here. If they ignored the bending of time, your map would drift by miles in a single day. We correct for it constantly, without thinking, every time we follow a route. Relativity is baked into the ordinary morning. And at the scale of the very small, the quantum scale, objects stop having definite properties at all until you measure them. That is quantum mechanics, the strange rule book of the tiniest pieces of the world. A particle can be in two places at once, a fuzzy blend called superposition, described by a mathematical object called the wave function, until the moment you look, and only then does it pick two rule books. One for the big, one for the small. And here is the wound at the heart of everything, the thing that keeps physicists awake at night. Those two rule books contradict each other. General relativity and quantum mechanics cannot both be right exactly as they are written. They work beautifully apart. Each one, on its own turf, has passed every test we have ever thrown at it, to more decimal places than almost any idea humans have ever had. Put them in the same room, and they start shouting. The equations spit out infinities, answers that mean this is broken. A black hole is precisely the room where they are forced together. Enormous gravity, described by relativity. Tiny distances, ruled by quantum mechanics. Both at once. That is why a black hole, even a made-up tiny one, is not a horror story. It is a laboratory. It is the one place where the two great theories of physics must finally face each other and settle their argument. So keep that in mind. When we ask whether the machine made a black hole, we are really asking something deeper. We are asking whether we can build, with our own hands, the exact spot where the rules of reality break. And to even ask that, we need to understand what that machine actually does. Picture a ring, a circular tunnel, 17 miles around, buried about 100 meters underground, running in a great loop beneath fields and villages and roads. People live above it and never feel a thing. Inside that ring, a pipe emptier than deep space, colder than the space between the stars, colder than almost anywhere in the known universe. Think about that for a moment. We built, on purpose, a place beneath a French field that is colder and emptier than the void between galaxies. Through that pipe, we fire tiny particles, protons, the little cores of hydrogen atoms, the same protons sitting inside every drop of water you have ever drunk. We push them with magnets, thousands of them, chilled until they conduct electricity with no resistance at all. We push, and the protons go faster until they are traveling at more than 99.99% of the speed of light. In 1 second, a proton in that ring loops around the 17-mile track more than 11,000 times. 11,000 laps of a 17-mile circle in the time it takes you to say the word second. That speed is not a detail. It is the whole trick. Because the speed of light is the hard limit of the universe, the one wall nothing carrying information can ever cross. As you push a particle closer to that wall, something remarkable happens. It does not simply go faster and faster without limit. It cannot. The wall is there. Instead, the energy you pour in has to go somewhere, and it piles up. Its effective mass swells. You are pouring in more and more, and instead of more speed, you get more heaviness, more concentrated energy packed into a smaller and smaller flash. Near the wall, a proton can carry the punch of thousands of protons at rest. Let that sink in. You take one of the lightest specks of matter there is, and by driving it against the speed limit of the universe, you turn it into a battering ram. Now take two of these beams, going in opposite directions around the same ring, and steer them into each other, head on. Two swarms of these battering rams aimed at a single point, at a chosen spot inside a giant detector, a machine the size of a cathedral bristling with sensors. Layer upon layer of them, they collide. And in that collision, for an unimaginably small sliver of a second, you get one of the most extreme conditions anywhere in the known universe. A dot of space carrying enormous energy in almost no room at all. For that flicker, that tiny spot is hotter than the center of the sun, hotter than a supernova, closer to the conditions of the newborn cosmos than anything else on Earth has ever been. We are, in a very real sense, recreating a sliver of the first instant after the Big Bang over and over, 100 meters beneath the farmland. Here is why that matters for our question. Gravity, the force that curves space, cares about energy and mass squeezed into small spaces. It is not just mass that curves space. Energy does too, because energy and mass are two faces of the same thing, and that is one of the deepest truths we know. Squeeze enough energy into a small enough spot, and space curves so sharply that it folds in on itself. That fold, that point of no return, is a black hole. So the logic runs like this, and I want you to be able to hold every link in the chain. A collision concentrates energy. Concentrated energy curves space. Enough curvature in a small enough place makes a black hole. Could a collision then make a tiny one? In ordinary physics, no, not even close. And I want to give you a feel for how not close this is, because the number is genuinely funny once you see it. The energy we reach is titanic for a single particle, genuinely a record for anything humans have ever built. But compared to what gravity needs to fold space at that size, it is laughably, comically small. We miss by a factor with something like 16 zeros after it. 16. That is not a near miss. That is trying to leap across an ocean and falling short by the width of the ocean. By the everyday rules, making a black hole in that tunnel is like trying to boil the entire Atlantic with a single birthday candle, and then being told you are not even in the right hemisphere, and while you are at it, the candle has gone out. By every rule we are sure of, it simply cannot happen. But there is a word doing quiet work in that sentence. Sure, we are sure of gravity as we have measured it. And here is the turn. Here is where it gets interesting. What if gravity is not what we think? What if, at very small distances, gravity is actually much stronger than it appears, and it only looks weak to us because most of its strength is leaking somewhere we cannot see? That is not a wild guess pulled from nowhere. It is a real proposal worked out in careful equations by serious people, and it points at one of the strangest ideas in all of physics: extra dimensions. Dimensions of space beyond the three you know. And if they exist, the birthday candle might be enough after all. Hold out your hand and look at the space around it. You can move up and down, left and right, forward and back, 3 directions, 3 dimensions of space. That is the world you have always known. Every place you have ever stood, every object you have ever held, has needed exactly 3 numbers to pin down where it sits. 3, no more, no less. It is so obvious we never even question it. Now here is a thought that took me a long while to sit with. I had to read it several times before it landed. What if there are more directions than 3? Not somewhere far away, not in another galaxy, right here, woven into every single point around your hand, right now as you listen, but curled up so impossibly small that you never notice them. Let me give you the picture that finally made it click for me. Imagine a garden hose stretched across a lawn, seen from far away. From up here, it looks like a line, 1 dimension, a thing with only length. But send an ant onto that hose, and the ant discovers a second direction you could not see from a distance. It can crawl along the hose, yes, but it can also crawl around it, looping the little tube. That second dimension was there all along. It was just curled up so tight that from far away it vanished into a line. Now imagine the fabric of space itself doing that. At every point, extra directions, curled so tight that from our great lumbering size we never feel them. We are the observer far away. The curled directions are the loop of the hose, too small for us to walk around. This is one of the boldest ideas in modern physics, and it comes out of string theory, an attempt to describe every particle in nature not as a dot, but as a tiny vibrating string with different notes making different particles. The way one violin string can sing many notes. An electron is one note, a quark is another. All of matter in this picture is music, and the universe is the sound of countless tiny strings singing at once. It is a genuinely beautiful idea. Now, I have to be honest with you here, because honesty is the whole point of this. String theory is not proven. Let me say that plainly. It is a beautiful, elaborate, unfinished piece of mathematics, and we do not yet know if nature actually uses it. It has made no prediction we have been able to test and confirm. Flag that firmly in your mind. Contested. Genuinely, openly contested. There are thoughtful people who believe it is the deepest description of reality we have, and thoughtful people who fear it is a magnificent detour, and the honest truth is that today we cannot yet tell them apart. But string theory makes a striking demand for its equations to hold together, to not collapse into nonsense. The universe cannot have only 3 dimensions of space. It needs more, 6 or 7 extra ones, tucked away, curled so tight we have never felt them. And here is a related idea, cousin to string theory but simpler, that you should hold beside it. Perhaps there are extra dimensions that are not curled tiny at all. Perhaps our whole familiar 3-dimensional world is like a thin sheet floating in a larger space, and everything we know, every atom, every star, is stuck to that sheet, unable to leave it. Everything except one thing. Now watch what that does to our black hole question. Gravity in these pictures is not confined to our three familiar directions. Gravity spills into the extra ones, too. It spreads out into all of them, leaks off the sheet, drains into directions we cannot point to. And that leaking could explain a mystery that has bothered physicists for a century. Why is gravity so absurdly weak? Think about it. Really think. A small fridge magnet lifts a paperclip off the table. That little magnet, costing pennies, beats the entire gravitational pull of the whole Earth, 6 trillion kilograms of planet, all pulling down at once, and the magnet wins. Every time. Gravity is pathetically, embarrassingly feeble compared to the other forces of nature. By some measures, it is weaker than the force holding an atom together by a number with 40 zeros in it. 40. That is not a small gap. That is a gap so vast the mind cannot picture it. Why? Where did all that strength go? Maybe it did not go anywhere. Maybe it is diluted. Maybe most of gravity's true strength drains away into dimensions we cannot see, spread thin across directions we cannot point to, and only a thin trickle reaches us here in our three. Gravity would then not be weak at all. It would only look weak, the way a river looks like a trickle if most of the water has been channeled off into hidden streams. If that is true, then at very tiny distances, before the dilution has room to kick in, gravity would be enormously, ferociously stronger than we ever measured. Strong enough that a violent particle collision, squeezing energy into that tiny realm, really could fold space into a microscopic black hole. So now the disaster film headline suddenly has real teeth. Under the right assumptions, with extra dimensions of the right size, the machine could in principle make one. And this is the moment people panic. This is where the imagination runs to the cosmic drain, the swallowed planet, the end of everything. So let us do the thing the panic never does. Let us actually follow the physics of what such a black hole would do, step by step, and see where it lands us. Because the answer is the most reassuring, most wondrous thing in this entire story. Imagine you have made it. A black hole so small it would fit inside a single proton with room to spare, thousands upon thousands of times smaller than an atom. A speck against a speck against a speck. Your instinct says it will grow. It will fall to the center of the earth and feed until nothing is left. That instinct is loud. It feels like common sense. Now let us check that instinct against the reasoning, because the reasoning says the opposite, and it says it 3 separate times from 3 separate directions, and each direction is independent of the others. First, consider how a black hole actually eats. Its reach, the size of its point of no return, the event horizon, that surface from which nothing returns, is set by its mass. And this thing is unfathomably light, lighter than a mote of dust, so its horizon is unfathomably tiny, far smaller than the nucleus of a single atom. For it to swallow a piece of matter, that matter has to pass extremely, extremely close to it, closer than the width of a nucleus. But here is the thing about matter that we forget. Matter is mostly empty space, overwhelmingly empty. If you shrank a single atom to the size of a cathedral, the solid part in the middle, the nucleus, would be a fly hovering somewhere over the altar, and the rest, the whole soaring building, the pews, the vaulted ceiling, the great windows, would be empty. Your hand is like that. This chair you sit in is like that. The floor beneath you is like that. Our tiny black hole would sail through matter almost the way a bullet sails through fog, or the way a grain of sand sails through a cathedral without touching the walls. It hits almost nothing, gathers almost nothing. Its appetite is very nearly zero. And even the gravity it drags along is so faint that it would barely nudge the atoms it drifts past. Run the numbers and you find it would take longer than the current age of the universe. Vastly longer, many billions of times over, to eat anything you could even measure with the finest instrument. That alone should slow your heart. A monster that needs more than the lifetime of the cosmos to gain a single microgram is not a monster. But there is a second effect, and this is the beautiful one, the one I still find hard to believe, even knowing it is true. Black holes are not eternal. They evaporate. Bring gravity and quantum mechanics together right at the edge of a black hole, at that event horizon, and something delicate and strange happens. The empty space near the edge is not truly empty. Quantum mechanics forbids perfect emptiness. It seethes with faint activity, pairs of particles flickering in and out of being, and out of that seething, the black hole slowly leaks energy. It radiates, it glows, ever so faintly, and in glowing it loses mass, and in losing mass it shrinks. And here is the exquisite part, the part that turns everything around. The smaller the black hole, the faster it evaporates. It is backwards from what you would guess. Big black holes, the giant ones out in space, evaporate so slowly that the number of years involved has more digits than there are atoms in your body. They are, for all practical purposes, forever. But a truly tiny one, the kind we are imagining, the kind smaller than a proton, would evaporate almost the instant it formed. Not in a century, not in a year, not in a second. In a flicker so brief it barely counts as time at all. A tiny fraction of a fraction of a fraction of a second. It would sparkle into existence and vanish in the same breath, leaving behind only a spray of ordinary particles for our detectors to notice. It would die faster than it could fall. So the monster, on inspection, is a mayfly, born and gone before it could drift a single hair's width toward the center of the earth. It could not menace the tunnel wall, let alone the planet. And there is a third argument, and I find it the most convincing of all, because for this one, nature has already run the experiment over and over for longer than there have been oceans, and we did not have to lift a finger. High up in the atmosphere, particles from deep space, cosmic rays, come screaming in far more energetic than anything our machine can produce. Some single cosmic ray particles carry millions of times the energy of our collisions. So much energy packed into one subatomic speck that physicists gave the most extreme one a nickname, treating it almost like a visitor, the sort of energy that has no business belonging to something smaller than an atom. A single particle hitting with the force of a thrown ball. They have been slamming into the Earth's atmosphere for 4.5 billion years. Into the surface of the moon, which has no air to shield it, for just as long, striking bare rock. Into the sun and every star, since the stars first lit their fires. Trillions upon trillions upon trillions of collisions, each one far more violent than ours, across a span of time so long that the whole of human history is less than a single blink within it. If those collisions made planet-eating black holes, the Earth would have been eaten long before the first fish crawled onto land. The moon would be a hole, the sun would be gone, the night sky would be empty. And yet, the Earth is here, oceans and forests, and you in your chair. The moon is here, marked and cratered, but whole, hanging in the sky exactly as it has for aeons. The stars are here, burning steadily overhead as they have for billions of years, patient and undisturbed. That is not a reassurance handed down from an authority in a white coat. That is the universe itself showing its working across billions of years in the plain and stubborn fact of its own survival. The sky has been doing this experiment forever, far harder than we ever could, on a scale we could never match, and the sky is perfectly fine. Now watch how these three threads pull together, because separately they are interesting, and together they are something else entirely. Follow the first thread. A tiny black hole barely touches matter, because matter is mostly empty, and the whole is smaller than an atom, so it cannot feed. Follow the second. a tiny black hole evaporates almost instantly. And the smaller it is, the faster it goes, so it cannot last. Follow the third. Nature has been making far fiercer collisions than ours for billions of years on this planet and on the moon and in every star without the slightest harm, so the whole frightening scenario is already proven safe by the sky above your head. 3 arguments drawn from 3 completely different corners of physics. One from the emptiness of matter, one from the marriage of gravity and the quantum, from the very evaporation that made these objects seem so mysterious in the first place. One from the raw, observed history of the cosmos written on the face of the moon, and every single one of them points the same way. Not one points toward danger, not one. They all point toward wonder. And notice what has quietly happened while we were reasoning. We started with a scary headline, and we have ended with a tool. Because think, really think, about what would truly happen if that machine ever did make one of these fleeting black holes. It would not be a catastrophe. It would be the single greatest discovery in the history of science. I do not say that lightly, and I want you to see why. Because this is the heart of everything. So let me lay it out with care. Remember the wound. General relativity and quantum mechanics cannot both be right as written. They contradict each other, they shout at each other, and the one place they are forced to meet, forced to work together, whether they like it or not, is inside a black hole where gravity is fierce and distances are tiny at the very same instant. That is the exact room where the 2 rule books must somehow become one, and we have never been able to look inside it. We have never, ever had a black hole to study up close. The nearest real one is unthinkably far away, thousands of light years distant, and a light year is the distance light travels in a full year, moving at the fastest speed anything can move, the speed of light itself. Thousands of those, we cannot go there in a human lifetime, or 1,000 lifetimes, or the whole span of our species. We cannot fly out and bring one home in a jar. The cosmic horizon of what we can reach with our own hands is heartbreakingly close, and a real black hole sits far beyond it. But if we could make even the faintest whisper of a black hole in a laboratory, right here, 100 meters under a field, and watch it evaporate, and catch and measure the exact particles it sheds as it dies, we would be reading a message sent directly from the one place in nature where the 2 rule books collide. We would learn whether extra dimensions are real, whether those hidden curled up directions actually exist, whether gravity really does leak. We would learn whether string theory is on the right track or a gorgeous, elaborate dead end. We would learn how gravity truly behaves when it is finally squeezed down into the quantum world, the answer to the question that has stood open for a century. The very thing that sounds like the end of the world would in fact be the beginning of the deepest understanding we have ever reached. That is the reversal. The monster is a messenger, and here is where it stands today. The machine has not, as far as anyone can tell, sent us that message yet. It has searched patiently through the debris of countless millions of collisions, sifting the spray from every crash for the telltale signature of an evaporating black hole, that particular unmistakable burst of particles flying out in all directions at once, a shape in the data that nothing ordinary would make. So far, nothing, not a whisper. And that silence tells us something too. It tells us that if extra dimensions exist at all, they are not the size, the simplest, most hopeful versions of the idea imagined. They must be smaller or shaped differently, or perhaps they are not there. That is not failure. Let me be clear about this, because it is one of the most misunderstood things about how we learn. That is the map being drawn. Every place we look and find nothing is a place we can cross off, a boundary we can sharpen, a guess we can correct and set aside so the next guess can be better. This is precisely how we come to know anything at all about the layers of reality we can never touch with our hands. Not by seeing them, by reasoning our way toward them, building the instrument, running the test, and letting the universe give its answer, even when the answer is a patient and instructive "not here." So, let us bring it home. We started with an alarming picture. A machine under the ground, a black hole made by human hands, a planet in peril, the stuff of 100 frightened headlines, and we did not simply wave the fear away and tell you to relax. We took it seriously. We walked straight into it, right up to the scary sentence, and then we kept walking into the physics behind it. We learned, first, that we never see any of these things directly, that all of physics is really the art of reading the movement of leaves in order to know the wind we cannot see, the star that dances around an invisible partner, the ripple in the fabric of space, the ring of fire around a darkness. We learned that reality comes in layers, the everyday scale where your intuition works and a dropped cup falls, the relativistic scale where space and time themselves bend and clocks run slow near heavy things, so slow that our own satellites must correct for it every hour, the quantum scale where nothing is definite until it is measured, where a particle lives in a haze of superposition described by its wave function in two places until you look. We found the deep crack running through it all, that general relativity and quantum mechanics cannot both be true as written, and that a black hole is the one room in the universe where the two are forced to meet face to face and their argument must finally be settled. We saw what the machine actually does, firing protons around a 17-mile ring near the speed of light, that unbreakable wall, 11,000 laps a second, cramming energy into a flash smaller and hotter than almost anything in nature, a splinter of the Big Bang beneath the farmland. We saw why ordinary gravity is far, far too weak to fold space that hard, missing by a factor with 16 zeros, a candle against an ocean. And then we met the wild possibility that could change the whole answer. Extra dimensions, curled up impossibly small, like the hidden loop of a garden hose seen from far away, or a wider space our whole world floats within like a thin sheet, quietly draining away most of gravity's true strength into directions we cannot point to. A possibility that lives inside string theory, which remains unproven and must always, always be called exactly that, contested. We saw that if those dimensions are real and just the right size, a tiny black hole stops being impossible and becomes, in principle, thinkable. And then we followed, patiently, what such a thing would actually do once made. Barely feed, because matter is mostly empty space, and the whole is smaller than the nucleus of an atom. Evaporate in a flicker, because the smallest black holes vanish the very fastest, dying before they can fall. And we let the sky settle the whole matter for us, cosmic rays hammering this planet and the moon and every star with far greater violence than we can manage for billions of years. And the Earth still here, the moon still whole, the stars still burning overhead. 3 arguments from 3 directions, one single conclusion. Then came the turn that makes this whole story worth the telling, that such a black hole, far from ending the world, would be a doorway, a tiny, precious window onto the one place where our 2 great theories collide. A way to test extra dimensions, to test gravity down in the quantum realm, to finally begin healing the oldest open wound in physics. The headline said catastrophe. The reasoning said revelation. And that, more than any single fact about protons or dimensions, is what I most wanted to hand to you today. The habit of walking calmly past the scary sentence and straight into the physics that lives behind it. Now let me be honest about what we still do not know, because that honesty is not a weakness of this story. It is the very best part of it. We do not know if extra dimensions exist. We have looked, and looked hard, and not found them, at least not in any of the simplest forms we hope for. We do not know if string theory truly describes our universe or is a gorgeous mathematical dream that nature, in the end, never chose to use. That question is genuinely wide open, contested, and anyone who tells you the matter is settled is telling you more than we actually know. We do not know what happens deep inside a black hole, at the singularity, that point at the center where our equations stop giving sensible answers and simply hand back infinity and break. We do not know how to join general relativity and quantum mechanics into a single coherent whole, one rule book instead of two that quarrel. We do not know what came before the Big Bang, or whether before is even a word that means anything there. We do not know whether our universe is the only one, or one bubble among countless others in a wider multiverse, and that too is contested honestly and openly. That is the great unfinished task of physics. Sitting there in the middle of everything, waiting for someone to solve it, perhaps someone alive right now, perhaps someone not yet born, someone who will first hear about all of this the way you are hearing it now. And I want you to feel, genuinely feel, how good it is that these questions are still open. A finished universe would be a closed book on a shelf, read once and set down. Ours is a book still being written, with the most important chapters still blank, and we, all of us, are among the ones holding the pen. Every collision in that ring, every measurement, every place we look and honestly find nothing is another sentence added to the page. We do not have the ending, and that is not a loss. We have something far better than an ending. We have the work still in front of us, and the whole strange, beautiful universe still waiting to be read. And so here is where the reasoning finally leaves us, standing right on the edge of what we know, looking down into the wide dark of what we do not. Beneath the farmland of two quiet countries, a machine hurls the smallest pieces of the world together at nearly the speed of light, chasing a whisper from the one place where physics itself runs out of words. It has not found a black hole. It may never find one. But turn that around. The very fact that we can ask the question at all, that we can build the machine, run the numbers, weigh the danger honestly, and come out the other side, not with terror, but with awe, tells you something quietly astonishing about what we are. We are the part of the universe that has started slowly to understand itself. Made of the very same particles we fire through that ring, reading the leaves, learning the wind. And the more I sit with all of this, the more the fear drains quietly away and something warmer and steadier takes its place. Not a drain that swallows worlds, a window that opens them. If this kind of thinking gives you the same quiet thrill it gives me, I would love for you to subscribe and stay here with us, because there are so many more of these questions waiting for us to walk through them together, one careful step at a time. Thank you, truly and warmly, for giving me your time and your curiosity today, and for being the kind of mind that wants to follow the reasoning all the way down to where it ends.